Okay, well, as we're waiting on a couple more people, if it's all right, I'm going to get going and just introduce myself and get the talk going. And I just want you all to know that this is supposed to be very informal. So if you have questions, feel free to ask. I want to share with you some of my enthusiasm for geometric deep learning. And I'm a computational geometer by training, and I come from a background in graph theory and computational geometry. I'm a fifth-year PhD candidate working with Joe Mitchell here at Stony Brook. Well, I say here, but at Stony Brook. And over the past roughly just over a year, I've found geometric deep learning, and I realized that while I wasn't originally a machine learning person per se, I found that us computational geometers, us applied mathematicians, we really do have a seat at the table in the deep learning literature. And I didn't know that until I really found this. And there's a lot of cool ways that we can lend our geometric viewpoints to help inform the deep learning literature and the current work that's going on. So that's something I want to share with you all. And I'm not assuming a deep background in machine learning for this at all. And if you have questions about any of it, if I'm going a little too fast, feel free to let me know. All right, I'll be sharing stuff off of my desktop, and then the audio and video is on my laptop. So hopefully this all works. Okay, cool. I see my slides. All right, nice. I'll hide this. Okay, so we'll be talking about geometric deep learning today and trying to understand neural network architectures. Now, before we get into that, I need to set the stage for what is deep learning, right? What are we trying to do here? So for the purposes of this talk, we're going to be speaking about supervised learning. You can think of this as function approximation. The setting here is to introduce some notation for convenience. D is some set of pairs. This is our training data. We have XY pairs, and these are vectors. And suppose they're IID observations. At the ground, we have this ground truth function f that describes a functional relationship between the x's and y's. However, we don't know what this function is, and we're trying to figure it out. Our objective is to estimate this functional relationship between the x's and y's. To do this function approximation, one often specifies a parameterized function class. So let's make this more concrete. Big F here could be the set of degree D polynomials. And then the theta would be the coefficient vector for the polynomials. And what we want is a function that agrees with the training data, and that's what I mean when I say f tilde needs to equal f of xi. So we want a function that agrees with the training data, D, and it's not too wacky, right? We want to have a regular function, and there's many different ways to describe the regularity of a function. Here I give two intuitive little pictures that can help you wrap your head around this. So the bottom left describes, it shows two functions that agree with the training data. They interpolate the data. You'll see this in the literature called the interpolating regime for machine learning. And the green function and the blue function have different levels of regularity. The green function is it's less wildly changing than the blue. The curvature is less on this green. So by many natural definitions of regularity, we would say that the green function is more regular on the left. On the right, here's another example, and now the green function is less regular than the black curve that's somewhat splitting these reds and blues. Okay, we'll gain more familiarity with the setting as we continue to move along. Now, in deep learning, our function class big F on the previous slide, that is the set of neural networks, or we're restricting ourselves to neural networks in deep learning. A neural network is just a function. It represents a complex, or well, it represents a complicated, potentially complicated function, not complex necessarily. But here I'm introducing a multi-layer perceptron, and this is one of the classics, right? It's in terms of neural network architectures. On the right, we see what's called a neuron. And what's going on here is we have an input vector of 4 scalars, and we multiply each of these input terms by another scalar, a weight, and then we aggregate. Maybe we aggregate by summing things. That's why I have a plus here. Optionally, there could be a bias, which is another scalar. So we are aggregating a bunch of, aggregating the input in a linear way, because we're just multiplying and then adding. And then we pass the resulting scalar through what's called an activation function, or a nonlinear transformation. So this is something like a sigmoid function, which, if it helps you, this would be like 1 divided by 1 plus e to the negative x, something like this. Now, all right, we structure these neurons in layers, and that's what I show at left here. So in layer 1, we have 3 neurons, layer 2 has 2 neurons, so on and so forth. What I want you to really pay attention to is that the way that this MLP is working is we have an input vector. Here it has length 4. We perform a linear transformation on this input vector to turn it into a length 3 vector. So here that's just left multiplying by a 3 by 4 real matrix. And then we have a length 3 real vector. Element-wise, meaning for each element in this vector of length 3, we pass each element into a sigmoid function to get this nonlinearity. So we will then have a length 3 vector coming out of this layer, and then we repeat the process. We do a linear transformation of that length 3 vector. So we're left multiplying by a 2 by 3 matrix, get into layer 2, nonlinear transformation, which we call activation, into layer 3, and then we return what's left over after layer 3 as output. That's what an MLP is. It's this fancy function composition. That's what's going on. So here are some takeaways. Entering each layer, we perform a linear transformation. If you have a bias term, then it's technically an affine transformation, but think linear right now, particularly because we'll be talking about group representations later, and this linearity is important there. Exiting each layer, we have the nonlinearity, and the nonlinearity is key, because to check your understanding, if we just had a composition of several linear functions, we could represent the whole thing as just one linear function call. Because, yeah, I mean, check your understanding with that, perhaps. Now, I should mention that multi-layer perceptrons are very powerful. An analyst would say that the set of functions that can be represented by multi-layer perceptrons are dense within the space of continuous real valued functions. So, okay, what that means in more accessible terminology is that essentially any function that we want to represent, we can do so with an MLP that has at least 2 layers, and with these layers being really wide, perhaps. So why not just stop there? Why do we have these other neural networks? Because training these MLPs is, in a sense, intractable, meaning settling on a good weight vector on those edges that I showed on the previous slide, that's really tough. And as a bit of a complexity theorist myself, I usually think of intractability in terms of time complexity or space complexity. Here, the resource that is scarce is that of training data, how much data we have. So for multi-layer perceptrons, as the dimension of the target function's domain increases, so as our input vectors are getting more and more elements, we're going to need an exponentially growing amount of training data to have a good theta that we can settle on. All right, I'm throwing around a bit of jargon here, but I'll solidify this with some more examples as we move on. But what I want to emphasize here is the intractability of only using MLPs once you have high dimensional data. Geometric deep learning, which we'll talk about, is going to make geometric assumptions about this function class, meaning how does a function class interact with different group representations, symmetry group representations. And this will allow us to make big F smaller. All right, now we can finally talk about geometric deep learning. Here's a cute little cartoon from Bronstein. And rather than just multi-layer perceptrons, now these are some terms you may have seen before, perhaps graph neural networks, convolutional neural networks, perhaps the most famous, recurrent neural networks, which include things like a long short-term memory model, the transformer architecture, the deep sets architecture. There's all of these out there, but what are the unifying principles here? That's what geometric deep learning is about. We want to avoid reinventing the wheel over and over. And a lot of these neural network architectures are really getting at similar ideas, but if we formalize things in terms of domain and symmetry, and we're very aware of the geometry at play, then we can better understand what's going on. I definitely invite you to go to geometricdeeplearning.com. Highly, highly recommend it. It's really cool. It's done by Bronstein et al. And like some of the people who came up with this, or the people who came up with this field. Okay, so we talked about regularity earlier, and I teased the notion of a geometric prior, which are geometric assumptions about our function class. I'm just going to mention a couple things to pay attention. If you have the ideas of symmetry and scale separation in the back of your mind as I continue, then hopefully that will help some concepts solidify and cement within your brain. All right, so we're going to be talking about symmetry and group theoretic terms, and then also scale separation, which we'll get to later. This is not going to have much meaning until I show you an example. But first, we need to talk about a group. All right, so this is probably the most abstract thing that I'm going to present to you today. So a group is a pair comprised of a set, G, and a binary operation such that the following four axioms hold. We have closure. So as we, you can think of the group elements G and H as functions, and the binary operation here as function composition. And if you compose, like G composed of H is still in the set of functions G, that's closure. We're assuming that this is the case. Associativity, we get that for free because we're talking about function composition. The existence of an identity function, the existence of inverses for each element of the group. This is the key structure here that we use to formalize symmetry. Let's make it more concrete. Groups can be represented using, well, like group representation is a way of, well, representing the group as a real matrix, an invertible matrix. So we have a linear, we've turned a group element into a linear transformation. We're representing it as such, such that this equality holds here. Here's some examples. Translation group. So this is sliding things around here in 3D. So shifting a point in 3 dimensions can be represented like this, using this homogeneous coordinates trick that you may or may not have seen. Rotation group representation in 2D, If you multiply a two-dimensional real vector by this, then you are rotating counterclockwise by theta. Okay. Symmetry. This is one of the essential ideas behind GDL. Symmetry groups are those that leave the domain on which the group is acting somehow unchanged geometrically. Now, how you define unchanged is where you can be a little creative, and that's kind of cool. For example, the translation group, you could, if you shift and some sort of element, and it's still, for whatever application you're talking about or whatever setting you're in, if it's still the same, then that, like, the translation group can be interpreted as a symmetry group. Same with the rotation group, the isometry group, permutation group. Here's an example of a permutation group representation. This is definitely quite abstract at this point, but I'll be talking about an example right now that can hopefully make this a little bit easier to unpack in your head. Let's talk about image data, and image classification is the task that we're interested in. So we have something like this 3 at right, and we want our function, our neural network, to say, hey, this is a 3. We have an image here. We want our function to classify the image as the target that is labeled with it, which would be 3. The domain here is a grid graph, right? So at each of these nodes, you have a pixel. And this pixel has a value defined on it called a signal. And this is a function mapping the domain to the interval 0 to 1. So this could be the amount of white you have in the grayscale image, right? So a 0 might be it's full black, a 1 might be it's a completely pure white pixel. So these are signals defined on a domain. And this is where we can maybe understand translational symmetry a little bit more. Imagine that you're like a little ant or something, and you can zoom in and you're placing yourself at this node in the graph, one of these nodes. Hopefully you can see my pointer. If you were to just look at your local neighborhood, you've got 4 neighbors, right? One above you, one below, to the west, to the east. If you were to move or slide yourself around, your local neighborhood is still looking the same, right? We have this translational symmetry. Here we're talking about this MNIST data set, and this is just a little bit more background on the task. We have these handwritten digits, and we want to classify to figure out exactly what these images correspond to in terms of a digit. All right, still trying to make this more concrete, because admittedly, the group theoretic terms are very exciting mathematically, but they could be a little bit abstract. For MNIST, for this data set, if you have a handwritten 3 in your image, this red is supposed to be an image, a grayscale image. If your 3 is in the top right, and you were to translate this 3 to a different portion of the frame, you still want your function to classify it as a 3, right? It does not matter where this 3 is centered within your frame. So we want our function class to respect that, so that as we translate our input, we don't want our function class to give a different output. We want our neural network to give the same output for all. If you take a 3 and you let the translation group act on it, we don't want that to change the neural network's output. So this is formalized in terms of group theory and representations as well. So the domain here is the grid that I was showing you, and we let the symmetry group, which is the translation group, act on elements of the grid. And here it's just shifting. And then you can infer, well, you can define an action on the signal space as well, where this is kind of getting at the difference between a domain and the signals defined on that domain. So the domain for image data would be a grid, like a grid graph, whereas the the signal space would be images, because you can view an image as a mapping from the grid to, if it's grayscale images, to the unit interval. Okay. This is getting at the notion of invariance and equivariance. All right, so I want to explain this in accessible terms here. So I want to zoom in right to these bullet points right away. A function f is said to be G invariant, where G is a group, if letting the group representation act on the function's input does not change anything. So think of our image example. As we have that 3, we don't want our function to change as we translate that 3 within the frame. So we want our function class to be G invariant, where G is the translation group. Equivariance is a little different, but it feels very similar. What equivariance is saying is you have your representation of a group element, which is, remember, group elements are functions. Think of rho of G as matrix. I mean, it's a linear transformation that's invertible. Let rho of G act on the input. If that is the same as just computing f of G, f of X, and then letting the matrix act on that, so if it commutes with elements of the group G, then that function is said to be G equivariant. Okay, I know it's not absolutely essential that these definitions are all like just cementing right away, but these are some of the key terms that you'll see as you go into the literature yourself, which hopefully you do. Let me give more examples here. Here's translation equivariance. This is what I was talking about above. So a convolution, what is that, right? A convolution can be defined as a discrete convolution. Oh, sorry, I lost my place. A discrete convolution can be defined as a linear function that commutes with elements of the translation group. Okay, what does that mean? It means that if I have my handwritten data, or if I have my image right here, and I blur it, and then I shift it, that's the same as if I shift it first and then blur it. And that's interchangeability of the shift and blur operations. That's what we mean. Think of this, if that equivariance definition was a little murky, think of this as equivariance. Okay, did I skip? Okay. So a convolutional neural network is one that is equivariant with respect to the translation group. That is what a CNN is, and that's its magic, right? It breaks the curse of dimensionality by ensuring that it is G equivariant, where G is the translation group. Meaning, convolutional neural networks shouldn't change their output as you translate the input. Now, technically, if you're really nitpicking, I just described invariance rather than equivariance, but we'll leave it at that without getting into the extreme details there. All right, now, what's the upshot? What are some takeaways here? The convolutional neural networks make the hypothesis function class f smaller. They are saying, we're only going to search within the space of convolutions, right? And that makes it tractable to train. We're no longer talking about multi-layer perceptrons in a much larger f. We have a smaller function hypothesis class now. What is convolution? Here's a little depiction. So we have an image data here. Say it's, well, this is not restricted to the unit interval, but say we have this grid with these integers on it. These are pixels. This 3 by 3 thing is called a filter or a kernel. And what we do is we want to slide this kernel across the image, and it's going to do this aggregation. Remember when I showed the MLP and I showed multiplication by a weight, and then eventually you aggregate with a plus, with a summation? That's what this is doing, right? But what's cool about convolution is that the weights are being shared. What I mean by that is the filter here, the convolution kernel, is the same as you slide it across the image. And MLP doesn't have this requirement that your weights are going to be the same, or shared weights is the terminology you'll often see in the literature. Now, aggregation need not be summation. You could maybe take the max or average. Those are other things you'll see: max pooling, average pooling. Convolutional neural networks are often deep. What we mean by that is that we'll take an image here, and then we'll convolve a filter over this image to get another image. And then we keep doing this over and over and over. And the reason why you want to do this is because you can then get at what GDL calls scale separation. Meaning you have this 3x3 filter and you're convolving that over the input, but you chain this, you compose it over and over and over, then you're able to sort of get at broad global signals rather than just local ones. I can make that more formal as we go on. And yeah, here's some more definitions about scale separation. What I want to do here is really emphasize this upshot takeaway at the end. So we say that a function is locally stable if downsampling, meaning you agglomerate nearby points, you treat them as the same, or you like merge them together, doesn't cause f to change uncontrollably. So we want this local stability, and this is useful because this is how depth works. This is why we make our neural networks deep. Here's how we can visualize scale separation, because I realize I'm throwing a lot of notation at you, and it can be maybe a little much, but we call this a coarse graining, where if we have our image data up here at the top, we have our grid omega, and then an image is just a mapping from the grid to say the unit interval if it's a grayscale image. Well, a coarse graining is we're going to agglomerate some of these grid points, right? We're going to, rather than having this many elements of our grid, we now have a smaller number of pixels. And this blurred the input. But blurring is good, right? Because imagine if you're trying to do image classification on something, and if you were to like blur your eyes as you're looking at something, maybe some of those signal processing people might call this a low frequency signal. Those can be very useful for when you're trying to classify an image, for example. And this generalizes to other domains as well. But we care about both the very precise details and also the broad global properties of something when we're trying to have our function do something such as image classification. So it is good to blur, because then we can kind of get at different scales of information. Here's an example of that. So we're still talking about CNNs here, right? Convolutional neural networks. But if you have an input image here in grayscale, we want to say, what kind of dog is this? Or, well, the network wouldn't even know that it's a dog necessarily. It would just say, okay, I'm given an image. I have to say, what is this image? Is it an orange? Is it an apple? Is it a dog? What is it? And we're going to perform convolutions on this and chain them together to just have a lot of function composition going on. And then we have some max pooling. They say max pooling. I was talking about sum aggregation earlier. And this just means you're aggregating or pooling. Those are synonyms. but rather than adding things, now you're taking the max. But here you have smaller or more, you have coarser images, and that can be useful because you care about different levels of detail when you're trying to classify this input image. So this scale separation prior is something very important in the GDL literature as well. Remember, we've talked about domain, talked about symmetry, scale separation. These things are the trifecta. Once you have this, now I'm going to hit you with some more notation, but this is the blueprint for geometric deep learning as stated in their in the Bronstein book that they're working on. So if you have these ingredients, a linear representation, remember we really like our group representations. You have a linear G equivariant layer. So that's a G equivariant function B. You have nonlinearities, that's that sigmoid function, if that helps. Then you have your pooling or aggregation operators, and then you might have an invariant layer as well to do like the final global pooling step. And the idea here is to build a G invariant function f by doing a bunch of function composition. I don't expect all of this notation to just immediately click. I just wanted to put it here for completeness. Let me give you more examples to, because I'm really trying to emphasize like the intuition here and how there's really cool geometric perspectives here that can be very helpful for the deep learning literature. We talked about CNNs, convolutional neural networks. They operate on grid-like domains such as images. But geometric deep learning designs appropriate architectures for other domains as well. You saw the CNN. So this is from Bronstein. They have this really nice table here. And there's many more architectures than just these. These are kind of just an all-star list, for example. CNN, you have a grid domain, and the symmetry group is translational symmetry. Spherical CNN, we'll talk about this in a bit. This is the special orthogonal group, SO3, which is cool. So now your signal is defined on the surface of a sphere. This would be useful if you're doing climate data, you're working with climate data, for example, because the surface of the Earth is the surface of a sphere, or close enough. Now, mesh CNNs, this is something I really am interested in. I like meshes. So here, your domain is a manifold or a discrete representation thereof, where you have a mesh that's representing a manifold in a discrete fashion. That's the domain. So this might be something like looking for lung cancer or nodules or things like this, where you want to look at some 3D modeling, and maybe you have CAD signals, computer automated design signals, and you want to classify, say you do an MRI of someone and you want to figure out, wait, this mass here, I want to classify this to, is it a danger that I need to just refer this to a radiologist immediately so they can check and use human expertise to see if this thing is really cancerous, or is it benign and I don't need to use the radiologist's time there? So like, that's one application of these like mesh CNNs. Graph neural networks work on graphical domains, and the graphs could be things like social networks. They could be transportation networks. Say you're talking about assisted driving, like autonomous driving, that's the word I was looking for, or something like this. Then the domain might be a graph, which is a road network, and the symmetry group for graphs that's relevant is the permutation group. And I'll get into that in a bit. But there's all of these cool architectures that if you look at them from a domain and symmetry perspective, you can really understand why these architectures are working. And we sort of did that quickly for CNNs. Let's look at graphs briefly, and I'll be less verbose with respect to notation here. I just want to get the main ideas across. So these are two graphs. At right, this is a molecule. I don't know very much about chemistry. Like, I know that Robert is a expert.
It's also a very popular molecule. It might be caffeine.
Ah, yes, that's right. I've got some right here. So yes, I believe it is caffeine. So I remember Bronstein lecturing about this. So that's cool. I'm glad that I have a computational chemist in the audience. But yeah, so you could have a graph would be this, and we'd want to classify and say, well, what molecule is this? And you could train a graph neural network to take in a graph that has node features, which these would be the atoms, or what type of, you could have edges as well, edge features, and that would pertain to bonding and things like this. And you would want to classify this and say, what kind of molecule is this thing? And that would be useful for many downstream tasks. And this is a popular application of GNNs. On the left, this is the Cora data set, which these are citations. I know that we have a lot of academics in the audience, so maybe all of us, but here we have papers that are citing other papers, and then they're color coded. I forget exactly what the colors correspond to, but you might be interested in predicting, all right, I just saw this new paper out there, who else is going to cite this paper? Or maybe it's a social network and you want to figure out who's going to follow whom, or who's going to retweet whom. So, or maybe how to recommend a friend or a prospective connection to someone. These are the tasks that GNNs can perform. I want to make a link here, no pun intended, to, or maybe definitely intended, to the CNNs that we were talking about earlier. So remember how we had the grid, and we had a filter that aggregates elements of the grid, nearby elements. We had like a 3x3 filter that was taking those pixels and like aggregating them and like bringing them together to form a new image, a new tensor. Here, GNNs have an analogous operation. We call this a GCN, Graph Convolutional Network. And here, now it's no longer the case that every interior node of a grid has degree 4, right? Or every corner has degree 2 on a grid, every edge has degree 3 on a grid. Here we might have different degrees, but we still want neighbors to aggregate, right, over layers. So this could be you in the middle, and you have your little features, right? Your I don't know, your major, your research interest, your age, whatever, your preferences on music or something. If maybe we're working for a music recommendation software. And you also have your friends within your network. Well, if you're friends with people, maybe you have similar music tastes or something along those lines. So you want to absorb from your neighborhood. This is a one-hop neighborhood. That's the terminology. It means you can hop to your neighbors here. And you want to propagate your friends' features into your own if you're in these functions. In these deep neural networks, you have this propagation because, and we can learn how heavily to weight different things as well, and how heavily to weight different friends. Maybe somebody is a strong friend and someone else is more of an acquaintance or something along those lines. And there's more complicated ways to do this as well. Attentional graph neural networks, message passing. But the idea here is that you want to use proximity, right? Who's nearby you? In images, it was, I look up, left, right, down to like the nearby images. Here, you might look to your neighbors within the graph. Here's a visualization of that GDL blueprint that Bronstein defines. Here's something, this is more closely related to my research. I've been working on learning an approximator for the TSP along with some others. And we are using a graph neural network to learn an approximator for solving the traveling salesman problem. And the input there is a complete graph with weighted edges. And what we will do is we use a graph attentional network, which was previewed a little bit on the previous slide. I didn't get into the details, but we encode the input into some latent feature space, and that's called graph embedding. Then you decode that feature vector back into a graph, and then you perform some post-processing on it. And this can give you an approximation algorithm for the TSP. This figure is from Joshi et al. But there's tons of applications for these graph neural networks. Okay, another thing, and this is a lot of a text to throw at you on the slide, but we can use this for climate prediction. Or we can use geometric deep learning techniques for climate prediction, for example. And this is a Quanta article, and it's talking about how good these so-called gauge CNNs are at detecting cyclones, which is it's really cool because it's performing image segmentation. So you've got images on the surface of a sphere because it's the globe, right? The surface of the earth. And you have these weather patterns moving over this sphere, and you want to highlight and track the areas that are tropical storms or cyclones and things like that. This is actually what I was just talking about, was work by Cohen et al. And really, we've got two different types of domains here that are show GDL's interesting properties and applications. This first figure is meant to depict the special orthogonal group SO3, which this is a Lie group, and so we're not even finite. But you can have these infinitesimal perturbations and rotations. So you're on a sphere and you can like twist it just by epsilon, so you have signals on the surface of a sphere here, and GDL is meant to deal with these domains. We can work with these. We call this a spherical CNN. Those are designed to operate on the surface of a sphere. Signals that spherical CNNs work with signals that map the surface of a sphere to a signal space. Now, Cohen et al., they took an icosahedron and said, well, heck, this is a pretty good discretization of the surface of a sphere. And it's regular, that's pretty nice. And so they then do a triangular mesh on the surface of this icosahedron. And for those of you who share my interest in polyhedra, the icosahedron has really cool symmetry properties. I mean, it's got like its symmetry group, I think, is of order 60. And you have all these different rotations that you can do that leave the icosahedron the same, right? I mean, if you've got an icosahedron and you twist it and move it around, then you still have the same icosahedron embedded in 3 space in the same exact fashion if you've twisted it in one of these 60 ways. So there's really cool group theoretic stuff going on here in terms of symmetry groups, and we care about the domain. That's what I want to emphasize here, is we really care about the geometric properties of the domain, and that's what's making all of this possible. That's how we break the curse of dimensionality in some cases. I mean, it's so hard to break that curse, but we can do so if we're really clever with paying attention to the domain. So here's some main takeaways here, and then I'll wrap up. First of all, neural networks are function approximators. We spoke about MLPs, which are multi-layer perceptrons. Those are universal approximators. However, training those is hard. And when I say training, just to recap, that means we have an optimizer such as a stochastic gradient descent. We'd be doing something like that to let the weights on our neural network converge to something that gives a function that approximates the ground truth very well. That's what I mean when I say training. That's really tough on fully connected neural networks. That's another way of saying multi-layer perceptron. Well, fully connected neural networks, maybe the difference between the two would be your aggregation or activation. But MLPs and these fully connected neural networks are tough to train because the scarce resource is our training data size. And you need tons of training data to train an MLP on a high dimensional input very well. Now, the key concepts that we talk about in GDL are domain, symmetry, and scale separation. And the tools we use are those symmetry groups, graph theory, which I really should have, I wish I could have emphasized how important and fundamental graph neural networks really are, because a lot of these neural networks can be represented as graph neural networks. I mean, if you squint hard enough, as Peter Velichkovich says, if you squint hard enough, you can see a lot of these problems as graph neural network problems. And then computational geometry is essential here. You really need to look at the discrete and computational aspects of your domain. And then how do we use GDL? Well, it's really, I mean, two main applications of this are to, if we got a project that we're trying to do, or we're trying to work on, we can select from the literature an appropriate neural network architecture for our task. Maybe we're doing molecule classification, or this is outside of my depth, but automated drug design. This is something that has been very popular in graph neural network pieces of the literature. I'm not familiar with that, but I know that it exists. And you want to suggest, like, okay, why don't we, here's a way to design a new drug, for example. And if you know your setting for your given task, GDL will help you select from the literature a good neural network, because you know to look at domain first and symmetry and scale separation to pick your neural network architecture. You don't want to just throw an MLP at everything. Or you also don't want to, it's very tempting, but you don't want to throw a convolutional neural network at everything. Now, the last thing GDL can do is, if you have this perspective, this lens, GDL will guide you to design new neural network architectures in a geometrically aware fashion. So you're looking at the geometric properties of the domain and the signals that are defined on that domain. So that's what I wanted to get through with you all today. And I really appreciate your attention and attendance. I hope that some of I know I was throwing a lot of jargon and notation at you, but hopefully some of the main ideas came through. So I'll open it up for questions if anyone has any.
Thank you very much, Logan.
Thanks, Robert.
Since you put a molecule up there, and it's interesting, you've got the icosahedral group as well, like the Buckminster fullerene C60. It's nearly every chemist's favorite molecule. And the rotational group has the 60 elements you spoke about, but if you include the inversions and mirrors and everything, I think you get up to like 120.
Right.
And so is it possible to make that extension? I mean, to basically include operations that are now non-local in their operation?
Yes. I'm very glad you asked that. So I'm not aware of how to do so on the surface of an icosahedron, but I do know for things such as if you're doing histology work where you have a slide and you're trying to classify the image data on a slide, then a lot of the time you care about this. If you were to flip the slide over, you still want your classifier to give you the same output. Right. As I understand, I'm not a histologist, but as I understand it, that's what they're looking for. So you can have these global actions that you want your function to be invariant to like a flipping action, for example.
Super cool. Yeah, one of the problems we have in chemistry applying deep learning techniques is that there's very recent literature showing that the neural nets people are using create artificial dissimilarities as well as artificial similarities between things, and so we've got lots of applications that are just imperfect right now. So this seems very relevant.
I know that there's a lot of work in that area of application of GDL to computational chemistry, and I mean that's not my area of expertise, but I know that if like there are answers there.
This is not just making a connection. So Marivi Fernandez, they're an IACS professor in physics. She's got one or more students working on applying deep learning techniques to basically create faster and more accurate computational models. So they're embedded now inside the simulation. And they've got lots of these issues as well. So if you want yet more problems to work on, then reach out to Marivi.
Yeah, that's cool. The applications here are really interesting. And it was nice because, as I said at the beginning of this lecture, I didn't originally see myself as a quote machine learning person, but I saw myself as a computational geometer and a mathematician and theoretical computer science belonging to those communities. But I now see that GDL and deep learning in general, it's quite a broad community. Everyone can really have a seat at the table. So it's pretty cool.
Absolutely.
Hey, I have one question actually.
Sure, go for it, Connor.
Can you hear me? Sorry. Yeah. I'm in. Yeah. First of all, the GDL stuff I think is extremely cool. It's especially for I'm in neuroscience, but especially for scientific problems where you can really justify a geometric prior. It seems like an amazing set.
I agree. Yeah. What sort of problems in neuroscience would be like things?
Oh, can you hear me now?
Oh, yeah, I can hear you again now.
All right, awesome. Yeah, sorry, it's something's broken with my AirPods. But the one question I had is you were talking about the example of convolutional neural nets, and you point out that convolution is equivariant under the translation group, or with respect to the translation group. But convolutional neural nets, the full network is invariant to translation, correct? And so just the GDL framework show the idea is that you can take a bunch of equivariant linear layers, the nonlinearity, the pooling operation, and then you have a final layer that actually has to be invariant, right? And you combine them to build an invariant network.
That is, wow, Connor, you hit the nail on the head there. That's an awesome question. So first of all, you don't have to have this G invariant layer at the end, this global pooling. You don't have to have it, but one of the key things is exactly what you were able to, the dots you were able to connect. So you have these linear equivariant layers and nonlinearity and local pooling, and the whole thing works out to be G invariant. And that's like the special, that's the magic. And if you were to look at the Bronstein et al. Book, so if you go to the www.geometricdeeplearning.com and you go to the book and you look through that, they'll give this some more discussion around where they talk about the GDL blueprint. But yes, I'm very glad you asked that. And so cool.
I always wondered that about CNNs. It never really made sense. People would always be like, yeah, it's convolution's translation invariant. And I'm like, convolution isn't translation invariant, but CNNs are. All right. That's really cool. I'll look at the website for sure.
Yeah, thanks for that question.
I also have a question. Thanks for the talk, Logan. It's very interesting.
Thanks.
It's not directly related to the content of your talk, but I think you mentioned that functions that can be represented by MLPs are dense in the space of continuous real valued functions. Yes. And since I'm interested in approximation theory, so I was just wondering if you would happen to know which topology is being put on the function space that the density is respect to?
So that is outside of my area of expertise. I know that there are a myriad of these so-called universal approximation results.
Exactly.
And, yeah, and as you know better than I do, I'm sure. But there's, yeah, the way I have looked at it is I have taken those results at face value, but I have not actually gone through some of the like nitty-gritty details of that. But I know that there are pointers to those results that you could find pretty quickly, like if you just did a quick Google Scholar search.
Okay, sure, thanks.
Yeah, sorry, I couldn't give like a more on point, detailed response to that.
My guess is that it's probably some kind of uniform convergence, but I suppose it might depend on the setting that they're in. Yeah.
Gotcha. Oh, sweet. I see in the chat. Yeah, thank you for mentioning that. Yeah, that's if you were, so one thing is that website, and then also, I mean, if you go on Google Scholar, you can see a lot of this literature. It's exploding. The original paper now came out in 2017, and I'm looking at it right now. It has just under 2,100 citations. So like you have in 5 years, over 2,000 citations, which is a ton, in at least from my field. So you have these things that are really, there's a lot of interest here, and there's some opportunities for people with various research backgrounds to get involved. Yeah, well, I really thank everybody for attending, and that's all I've got. My email, I'm going to put my email in the chat in case anyone wants to reach out. Stony Brook. Cool. So if you have any questions or follow-ups, feel free to send me an email, and thanks for attending.
Hey, thank you. Bye. Bye, everyone.
Bye.